Good afternoon to everyone here. We will begin the session. I am Arun Kumar, who is from 𝐑𝐴 Technologies Private Limited, and we talk about today such cutting edge technologies, which is nothing but machine learning. But today, what all I'm going to do is the mathematical aspect of some of the important concepts of machine learning. So, which is nothing but model selection and boosting. So coming to model selection and boosting, which is again such important topic, as you know, in industry recently, machine learning has been kind of started revolutionizing across industries. I would say starting from the healthcare, education, and so on and so forth. The machine learning is being cutting edge technology. It is revolutionizing every sector in the industries. So I would say, coming to the machine learning concept here, what we are going to talk about is all about mathematical aspects of it. And as we have the machine in the industry, the machine learning workflow, starting from having the project workflow, the project setup, and moving ahead with the data pipeline, where we build the data pipeline, that includes data cleaning and data pre-processing, and there are many different stuff like data collecting, annotating, cleaning, and also as a part of data wrangling, where there are many different stuff that are being needed for the as a part of data pipeline. I would say, so again, we would have to consider many things like data availability, user data, how we go about storing the data, and the data pre-processing, and the challenges handling such data. And this is all about the data pipeline. And moving ahead of the process of the machine learning, the project that is being held in most of the companies, maybe also the Google, like the world tech giant, are also using such kind of technologies as a part of the workflow, project workflow. The next one would be the modeling. First, we start with the project setup, and then moving on to the data pipeline, where we build the right pipeline for the model that the world is expecting. The industry, the customers are expecting the such kind of product, through which we get to go to the next stage, the modeling. That is where the model selection comes in place. Coming to the model selection, and in the modeling stage, we see during the modeling, the process, we see model selection, model training, model debugging. All these are part of the modeling process we call. And the machine learning modeling, primarily, we get to start with the problem. So most of the problem can be framed as one of the common machine learning tasks. Maybe so familiar, people may be familiar with some of the common machine learning tasks, but typical approaches to solve such problems will be such useful. And starting from figuring out the category of problem, whether it is it a supervised or unsupervised learning, is it a regression problem, is it a classification problem, does the problem requires generation or just a prediction. And these are all actually the way we go about selecting the model. Here we go for today's agenda: model selection, need for model evaluation, resampling techniques, hyperparameter tuning, metrics for evaluating regression models, and at last metrics for evaluating classification model. So moving further, we would call models, we would say model selection is such important stuff. As I was talking about in the industry, we get to select the right model first. Before even we get started with the modeling process, the model selection is such important, crucial step in the workflow process we call. So that is being important, modeling being an important component of the machine learning project. So we call here the model selection is, of course, it's a part of modeling, machine learning modeling. So here we go, select the right model that are, that is very much important when we go about selecting the model. Here we go, this is how actually the slides that has been made here may not be industry standard, but still, in order to understand the audiences, how they go about. But I will also use certain industry, what do we call the terminologies, the standard terminologies. Model selection is again part of the process of choosing the best model. Again, we would say the right model, depending upon machine learning approaches, otherwise called as machine learning methods. There are various machine learning methodologies that are available every year. The industries get to update, the lot of machine learning methodologies and approaches. For example, even recently we have seen OpenAI recently launched GPT-3. That's again a different machine learning approach, I would say, the machine learning method. And coming to parameters, we have again different parameters to talk about. The parameters of such model selections, or like it is about how we gonna yield the result through such model. So the results are interpretable, or they simple, or they accurate, or they scalable, or they fast. How fast it is, and how far we can scale that model to an extent. And again, that is again a part of modeling, the process we say. So coming to accuracy and interpretability, which we see here, they are again trade-offs. When we go about tune our model, and I mean select a model for the accuracy purpose, again interpretability we lose it. Neural network like machine learning algorithm, which is actually a very base for the deep learning, that actually loses. The people call it a complex model because it is hard to explain. What happened. What is happening inside the model, how how the customer has yielded such result from the model. That's again, coming to the interpretability and explainability. So based on these parameters, we get to select the right model. And then moving ahead in the process, we go for the model evaluation. So this is where again, why we need the model evaluation. Let's get to think about what is model evaluation. So we build a model, we selected initially a model, and we train the model. How are we going to train the model? It is everything about evaluation metrics that we focus towards. And what happened to happen here, if you ask me. So when we choose the right evaluation metrics for the task or use cases that we wanted to solve, so where we get to see model evaluation is basically evaluating the chosen or trained model. And again, model evaluation here falls in different stuff here, which I mean to say that typically model evaluation will not happen with the training data sets. That is what here stated here. The model evaluation with the data used for training is not accepted in data science, it is mentioned. But of course, machine learning, data science, and all of them are they are actually kind of in the same set. They are in the same set, we could say, even though they are intersected, but still they have the relative use cases. And this is how things proceed in the but coming to model evaluation here, why such data, the training data set is not used for model evaluation? Because what happens is we get to generate over optimistic and overfit model. So what does it mean, the overfit model and over optimistic model? Let's see in the following slides. So this is how we get to have the underfit model and again overfit model. And once we have the right data set for the model evaluation, that is where we see the best fit or good fit model. So let's as we go on, let's see what is all that. And these graphs are just representing the values against the time. And I mean timing in the sense the training time and the values that are yielded by the model. So these are the stuff we could talk about when we usually train a model. Like it's everything about the time constraints, because of course the performance constraints and compute constraints are such important, because we get to choose the right hardware accelerators such as NVIDIA GPUs, Google Cloud TPUs, of course Intel CPUs are also sometimes used, so on and so forth when it comes to it. And coming to underfit model, let's see. So why do we get such underfit model? It's again when we go on to see such underfit or overfit, it's again the trade-off between bias and variance trade-off. So we see it here. What happens, the model get to become so simple to describe the predictions. Of course underfitting models provides us such a low accuracy, because what we do is we get to do it on both testing and training data. No, we should not do that actually. But not just on the training data, but also on the testing data, we get the lower accuracy, because what we did is we did not choose the right data set that needs to be used for evaluating the model. So if you ask me what is the data set that you are talking about that we need to use for model evaluation, we'll go ahead and see that in the following slides. So here again, So too few examples, to train the model, which means to say the examples are nothing but the samples, the data. We get to have, we may be using very less data to train the model. That's again, the big reason, the cause that yielded such underfit model, I would say. And moving ahead, machine is unable to find the relationship between the data because we haven't properly chosen the data, to whom, to which we have to, go on to evaluate the model. Poor performance in training model, it is again happening because we do not evaluate properly the model. So everything is, again, we talk about, because evaluation metrics, it's such important upon which we train the model. So let's move ahead with the what is that, go ahead with the next one, good fit model. We are sometimes in the industry, they also call it as a best fit model, but trained model, such trained model will have here the right relationships between the predictor and outcome. So here, actually, the predictor and outcome here is mentioned for better understanding, to make a better understanding of the audience, to make them understand better. We have chosen these terms, but again, industry terminology is again quite different. We call such predictor as a features. The features and labels we call, and again, so that the trained model gets the future outcome, the correct outcome. So which is nothing but the right labels that we expected to yield. So, and again, moving further, so the model stays, this type of model stays between underfit and overfit, because we get to because we have chosen the right data set for evaluating the model. So this is again the point just before the error on the test data set, and again it's again a good skill to on both training and unseen data sets, which means that we get those the same result as we have done with the training data set, and again with the new data set. For example, let me take the industry example here. For example, we have fit the model with the help of the training data. For example, let me take the healthcare use case here. So let's take a COVID case here, COVID-19 data set we had. We are using part of the data set as a training data set, and we select the model here and we train the model using that training data set what we have selected. And again, we have such trained data set, and again we get to evaluate on the validation data set. That is, again, we get to learn such stuff as we progress here. Once we have such right model and we go on to ingest the new data set, that is nothing but unseen data set. So when we ingest such new data set to the trained model, it get to have the the right outcome what we have expected, the actual outcome, and we call the expected outcome. So this again we'll go on to see that. So moving ahead, the overfit model. So again it yields the same low accuracy. The other model what we have seen previously, quite before this good fit model, which is nothing but underfit model. The same way we also get here the low accuracy for this the overfit model. Why it is overfit? Because we get to train on the training data so much, and it yields the higher accuracy on the training data, whereas when we go on to test it on the new data, which is nothing which we call it as a testing data. So usually where we get the lower accuracy there, because there are again the real industry use cases when we talk, and experiences, and again the Kaggle-like competitions where we see such data. It's again a different stuff, I would say. So initially when the competitions in the Kaggle, what happens when they release the data, they release the training data set as well as the validation data set for training the model upon the given data. And what we do, we evaluate the model whether we have trained the right model. To check to evaluate the trained model, we get to use the validation data set. And upon such validation, we get to have the right good fit model. And when we test a model with the testing data, that won't be released during the competition. When we talk about the Kaggle competition, upon the result release, they get they take our models and they test it with the testing data, and that is where we get the result. Okay, and it is all about cross validation and stuff that we go on to see what is it. So again, here we see model error, and again too few examples to train the model, and training data again contains noise here, and these are all the costs, I mean the cause and reason why we get to yield such overfit model. Also, because of too much of noise and data model not able to recognize and categorize the needed result. And again, next one here, this is the technique we call in machine learning the resampling technique. So such resampling techniques are used primarily to split the data sets, the right data set. For example, training set data sets, we otherwise call it as dev data sets, development data sets, and that is where models are trained and models are developed, I mean built, and we get to select initially the model, and then we also split the validation data set here for the model evaluation, and we also sometimes take up the split the test data set here. So we do split such samples. I mean the samples are nothing but the data samples what we have taken to split the data. So as we see, such techniques helps us here in splitting the data for the machine learning processes that help us go forward in the process in the further stages. One among them is cross validation, which is widely used in the industries as well as in the Kaggle competitions. So, and what happens, Bootstrap is again different stuff, and we also sometimes use it for bagging purpose here, I mean in the machine learning. And again, coming to cross validation, this is how we get to choose resampling procedure we use. It's again a resampling procedure to cross validation, and it is primarily used to evaluate the machine learning model. Previously I used to talk about it, right? I was talking about it, right? So we cannot test, I mean we cannot evaluate the such machine learning model with the training data, but with the validation data. But how we go about split such validation data set, training data set, and such things are quite possible with the help of these techniques, the resampling techniques. We use such resampling techniques here to split the training data and the testing data as well as the validation data. And as we get to split it, and what happens, we go on to get the right results. So, and again, bootstrapping is another method, and we randomly sample the data with the replacement. With the replacement in the sense, we don't reuse that the data, but again, in place of that the existing data, we use the new data. And again, this is how we randomly pick the data from the data distribution on the data set. And this is again the method where we get to sample the data, resample the data, and split the data, I mean to say. So we usually use this method when we have a smaller data sets. So when we have a smaller data set, that is where we get to that is where we use this kind of bootstrapping methods. And again, number of sample needers are also can be decided with the help of this one. And again, size of all samples and test data again should be the same when we opt this kind of techniques. I mean, say the bootstrapping technique, what I'm talking here. And again, data from data sets are again randomly selected as I have just told you. So for each sample, and then we get to resample it, and then finally we aggregate everything. We also call it as bagging. And what we do here is we build different models upon the bootstrap data, and we ensemble such data by bagging options, and we get aggregated result. And we of course what happens, we get to choose as a result high voted samples are mostly here considered. So yeah, the next one would be, it's a very important topic. So here we are not talking about any practical or in-depth theoretical stuff, mathematical concepts, even though we talk a little bit, but we don't talk here the practical, what is that, how we go about implement such mathematical or theoretical concepts of machine learning. machine learning is all about mathematical stuff, right? So of course everybody knows that with no mathematics we say no machine learning, or say no deep learning, because machine learning is, has a kind of four pillars we call, mathematically speaking. So we have here, statistics as a base, and followed by that we have linear algebra, and followed by we have probability, and then finally we have the calculus that comes in place, and again calculus as a multivariate calculus. And these are the four mathematical stuff we get to choose, we get to work on in order to theoretically prove the concepts in machine learning. But coming to practical in the real world, we are the people in the research industries, and like for example Google AI, I would say, because we are as a 𝐑𝐴𝐵RAINS, we are partnered recently with the Google Cloud, as a technology partner, not just with them, and also as a NVIDIA, with the NVIDIA AI and other top technological companies in the world. And where what we have realized and seen from them, they are all developing the frameworks like TensorFlow, and that has recently, not recently, quite long ago, they have acquired Keras into it as a deep learning high level the library and APIs, I would say. So such APIs, we create APIs that implements such theoretical concepts what we do here mathematically, and basically C++ helps for that. And moving further with the Python, that often used as a APIs wrapper classes, and such Python is being the industry dominant language here. Because why it is dominant? Because machine learning, such data science stuff and the deep learning stuff are mostly implemented with the frameworks like say scikit-learn for the machine learning, classical machine learning, and Keras for again the deep learning, the tasks, we would say deep learning algorithms. And again PyTorch from Facebook AI, again it has become such a dominant options for the research industry people. So research people get to use this PyTorch very frequently. So hyperparameter tuning is again an important stuff when we talk about it. Why? Because we have seen AutoML that has been released from Google Cloud in the 2018, in the year 2018. And what happened? We have been seeing a lot of research that popping out everywhere from the industry, in the companies here and there, as an AutoML libraries and AutoML packages. And what people there do is just they play with those hyperparameter tuning. What they do is they automate this hyperparameter search. What they do is they do neural network architecture search. So we call in short NAS. And also recently transfer learning actually being such dominant, because taking from the research. Because again coming to prediction and research, it is again quite different. The goals of research is of course very different from the goals of prediction. And people who tend to work with the predictions, what is that, the machine learning, what they have to do is they need to have the prediction goal in mind instead of the research purpose. So again the purpose is very important here. So as we see here hyperparameter tuning coming to this point, so finding the parameters, such important parameters as a part of algorithm. This main purpose to find such parameter is to get the high precision and the accuracy. Again, if you ask me what is that accuracy, it is again a metric we call evaluation metrics, or maybe performance metrics we call. And such metric is used for evaluating the model. And that is why we call it as a performance metrics or error metrics or performance metric, where what we do is that is usually that controls the learning process. And we have types of optimizations here. As a part of hyperparameter, we get to have different types of optimization techniques. So which of course falls under this hyperparameter tuning. The one is manual search, grid search, and random search. So here So what is this? I was already talking about such neural architecture search. So basically, which means that get to choose, we are here to choose the right parameters such as learning rate, and there are again different stuff we say, epochs, and there are again whether it is, there are again various, like learning rates that I have talked about it. And again, one more important thing is how we go about the optimization techniques. So again, there are again quite different algorithms we have, like stochastic gradient descent and gradient descent. Usually SGD is used for the large scale stuff, but those are all kind of and again loss functions, and using the right loss functions and optimization functions and the learning rate, and all of them are current, basically we call hyperparameters. And when we chose it correctly, the right parameters, and we of course get the right the results, which means that we get the high precision accuracy. So usually what happens, accuracy, as we go on in the further slides, let's see that. So manual search here, so we manually choose the hyperparameters here. How we go about do that, it is like we do it based on the experience that the machine learning methods get to experience. So in the sense, based on experience, in the sense, as we see what is happening in the system, whether it is coming up with the right result, or did we choose the right baseline, and so that we get to build upon such baselines with the complex components where we can add on, where ultimately that gets that is where it becomes the complex models. And upon that is what we mentioned here, the upon experience. So here we go. Steps in such manual search are nothing but usually selecting the parameters, right parameters, and then training the model. And again, training the model is of course happens after the model selection. That is actually part of the machine learning modeling. And then moving further, we would say the evaluation, model evaluation. So model evaluation comes as the last part of the workflow. I mean the process of modeling. So next one would be the another type of, which is nothing but the grid search. So what we do is we go on to choose the parameters, the hyperparameters as a subset space. The grid, we move grid wise here. Instead of manually picking the hyperparameters based on our experience with the model results, or, and here what we do, it is again, manually, chosen, but instead of choosing one hyperparameter or another one, we get to choose the subset of subset of hyperparameters. So actually we get to move by grid wise here. So grid wise we select, like we go with considering the set of parameters that are needed, and we note all the accuracies that are with a different set of parameters, and we evaluate them by combining all of them, and then we take the highest accuracies from the combination. And this is all, these combinations we call usually as a bagging and boosting stuff, we ensembling methods that we see in the for the slides. The last part of it, we will be getting the values, that is that gets placed in the form of matrices. That is where that is why we call it as grid search. We go on to search grid wise. So where do we do this? If you ask me, it is all, everything is happening on the data distribution, the data set. So data set is as a given as a sample, and we get to work with such data sets, and we go deal with them such strategically. And here we see a random search here, process to find. It is again widely chosen technique in the industry. Process to find the best parameters. Again, we use instead of manually searching the systems itself, it get to choose randomly the combinations of such parameters on its own. So like this in the machine, in the diagram, it goes on to take randomly the the data distributions, the parameters, so the right parameters for the training the model and evaluating the model. So because why you kept on talking about this training, evaluating stuff, because that is a part of the modeling. And we also have another one which is called debugging, but usually people don't do that because that is which is quite hard. And in the industry, people, the experts, used to do it. We are at 𝐑𝐵rains, we are spending our time in most of the time also on the debugging space. So as a part of the modeling, machine learning modeling. So again, execution time of such method again depends upon the dimensionality of the data. So again, we get to have a 3D data. I mean, again maybe different dimension data dimensions we have here. And again, so how what I mean, usually it's this type of stuff works with the the lower dimension data, which is nothing but the 2D dimensions. So, and what happens after this? We use again the optimization techniques that I've told, that I've just told for the back propagation for neural network, and again gradient descent, and there are quite different optimizations that are available. But we use such optimization techniques in this method of random search. So again, moving further, this is again, when we talk about machine learning, again, I'm supposed to talk about these different types of machine learning, and one is supervised learning, another one is unsupervised learning, and finally, the reinforcement learning. So coming to supervised learning, we would say, of course, what happens here, supervised learning is very much, it is also having a lot of limitations. The supervised learning is a kind of machine learning. What it does is it chooses it, it has both the features and labels in it, which means that features are nothing but often called as inputs, and labels are otherwise called as output. And what happens, unless otherwise we have the label, we cannot do such supervised learning. And again, as a part of supervised learning, we have classification tasks and regression tasks. Regression techniques you basically used for the continuous data. On the continuous data, for example, house prediction, house pricing prediction, where what happens there the data what we get to use for predicting the house price in a given space, given place. So what we do is we get to choose the continuous data instead of having the categorical data, the categorical values. So usually such continuous values and continuous data we use for such regression, because regression values are just regression methodology here that get to yield the value, quantitative values like continuous values instead of the categorical values, say categorical values in the sense, say binary classification when we talk about the classification stuff. So tasks, such as whether the person is affected by this disease or not. For example, when we talk about the healthcare use case, whether this person is affected by the diabetic retinopathy or not. So again, we have different labels for diagnostic. So such labels, we use it here for finding out the output. Again, that depends upon the features what we take. When we do not take the right features in place, and again, feature engineering is such important stuff here. What happens with that feature engineering, when we go about doing the deep learning, everything gets automated. And again, usually data scientists, most of the time they get to work with such feature engineering tasks too. And again, coming to such regression models, let's see what are the evaluation metrics we use to get the results of that such models. So in the industry, we see predominantly chosen by following metrics. So actually, it is again integral part of model development. Unless we have such metrics in place, that is actually the target stuff we look into. I mean, towards. So when we develop such models, because we don't know upon which upon what thing we have to train the model and what would be our expected stuff and how we go about having such expected results, and all that happens through this metrics, error metrics we call, performance metrics otherwise we call, and it's also known as evaluation metrics, because it gets that is how the models get evaluated that we are training. that we are training as a part of the modeling process. So the next one, the mean absolute error is again such important metric we could call, and root mean squared error, or MSE we call, and in short, and again mean absolute error we in short we call MAE. And again we have mathematical stuff that is given for all this, and RMSE is again predominantly and most used error metric in the evaluation model, in what is that in the while we go about evaluating the regression model. So again RMSE is such important. Again, median absolute error is also important, but we don't usually use such frequently like RMSE and MAE. And coefficient of determination, otherwise called as R squared, and this is also used very much, but let me go ahead and talk about this RMSE, because that is being predominantly used in the industries. Let's see what is it. So RMSE is nothing but we have that error, and how do we get to what is that? How do we get to yield such result? How do we get that error? If you ask me, we have the target variable, also the expected, what is that actual variable, what we have got the results, and we do the difference there, and what we do upon, the square of difference we do, and then we take the mean of it, right, of course, the average of the the difference between the target result as well as the actual result, and that difference we take the average with the total number of data. So such average we call it as a mean, and as we do the square root for that, the mathematical equation, and we get to yield, that is where what is that root mean squared error value. And typically what happens whenever we have the lower error, lower value of this RMSE or MAE or R squared, so we call it a higher accuracy model, we call higher precision, we call a high performance model. When the error values are higher, when it is higher, what we say is then we usually call such models or low performing model, because it has a lot of errors. So that is why what we do, we do not we do take the less value of the metric that has been through which we have got. So the next one would be metrics for evaluating classification model, and here we will go in depth talking about different types of evaluation metrics, or maybe otherwise called as a performance metric, or otherwise called as also known as error metric. And what we do here, we do it for the classification task. For example, classification task, as I've already talked about it. Let's take another example from the industry. Let's say simple example. We take a cat and dog here, and we take apple and another fruit, so say maybe orange. So how do we get to categorize them, to classify them? So this is the result would be here again, the categorical results we get, the values, which means that for example, we fetch the data, say apple there, apple image, or maybe, as I was saying, another example, the dog image. And what happens, the model provides the result, say 0 or 1, when, and again such what we do, we go on to label such for dogs we label 1, and for a cat we label 0. So whenever dog image is fetched there, when we ingest that data to the system, what happens, we get the 1, and which means that the result is correct. And what happens then, and from which what we get to know is, we use the right evaluation metrics, because unless we use the right evaluation metrics there for classifying the task, the use case, the use cases that rely on the classification task, and where when we don't use the right metric there, we will not be able to get the right result there. And again, data is also important stuff. When we don't build the data pipeline right, of course, the model, what that causes, the model, poor performance of the model, not getting the right results from the model. So here we have different types of evaluation metrics for such classification models, I would say. So here when we go about doing that, what we do, we usually select, we go first with the confusion matrix, because that is where what happens, we theoretically speaking, the mathematically speaking, there would we call a threshold value. What do you mean by threshold value, if you ask me? Again, we choose a value in the graph, that is where we see graphically, visually, and that is where actually the training gets begun, and the value of the model, I mean to say the accuracy of the model getting increased, the performance of the model getting increased, and we choose that value between 0 and 1. So 0 will be the lowest threshold value and the 1 will be the highest threshold value, and we get to choose the fixed threshold for this type of evaluation metrics. So that is why the confusion matrix, what happens, let me talk about it once we go further. So let's see another types of evaluation metrics here. The another one is ROC curve, and which is again very much popular. And again, AUC curve is again such widely used, and it has been used in healthcare sectors, and again it has been used in various other sectors too. And why I often talk about healthcare, because currently we are working on confronting COVID-19 use case, where we get to use the healthcare use case stuff. So that is why I'm talking about that. And again, if one score is important evaluation metric, I would say that is also being used widely, opted one like AUC. And these are the evaluation metrics we usually use for classification models. So I mean to say, while evaluating such classification models, we use these performance metrics or error metrics, we could call. So going further, today we're going to talk further about the confusion matrix. Let's talk about the confusion matrix. So this is again the it gives us the way in which what happens, the models are confused. Classification models are confused while making the predictions. So I'll give you the example. What does it mean? So it summarizes the prediction results from the classification problems. For example, we have different stuff when we talk about the the confusion matrix. The one would be a true positive and true negative, false positive, false negative. And these are the important thing we consider. And such a true positive, we call it as a specificity, which is also otherwise called recall. Okay, so true positive we call, and let's see what is that true positive and false negative and all that. But coming to healthcare like use cases, what we do is we should target that we will never ever get to have the false negative in the healthcare use cases. Let me talk about it as we go on to see what it is, and we get to know the prediction results. And these are the different types of prediction results that we are going to summarize as a part of the classification problems, and from where we get such results. We place such results in the matrix, and usually the confusion matrix are otherwise called as error matrix. So not metrics, matrix. So confusion matrix are also called as error matrix, because we usually mention the errors over there in the matrix in the table or manner of, so that they get to work very efficiently. When we talk about confusion, matrix is actually a type of evaluation metric. So metric is the one upon which we train, we evaluate the trained model. So basically, a metric mean we have a value. Basically, I would say accuracy is a metric. What do you mean by accuracy? That is again a type of evaluation metrics we call, because it is very similar to confusion matrix. But coming to accuracy, what is the difference between that, if you ask me? So accuracy is nothing but the true positive divided by the number of the prediction results. I mean the total predictions. So the ratio, I would say, such ratio we call typically metric is a value, but what we do is we gauge the system, we measure the system through such a value, and such measurement we call a metric here. And through such metric, what we do, we get to see whether we have got a high performance model, or whether we have yielded the high performing result, or whether we have got low accuracy. And that is what we say here. And again, we have mathematically proven formula and theoretical equations that are available for each of the metrics. And of course, what people did, and like scikit-learn, which is actually one of the widely used Python framework, the machine learning, classical machine learning framework, library also people call it, and where we get to see all these implementations. I'm talking about so many stuff here, say AUC, and a lot of stuff. I've talked about the regression and all that, and you would see such metrics and all of them getting implemented in such scikit-learn. I'm just giving you the simple example, because why I'm giving you this scikit-learn is that is where people learn practically applied machine learning, I would say, because people may not very much keen in mathematics, and people who are in research, of course, what they do in the research, they do see. So key to confusion matrix here, what does this confusion matrix does? So it does summarize such incorrect and correct predictions as a class. This is how, for example, fire alarming system. So what we do here in the fire alarming system, the system should alarm correctly whenever there is a fire in a place. So what happens here, so we see here when there is no alarm, when there is no fire, there should be no alarm, right? So but what happens here, we see there is an alarm but there is no fire, but still we have got the alarm. What happened there? We see the system is, we trained the system wrongly, and we evaluated the system wrongly. That is why we have got such wrong results. So, and we see here this table, and it looks like, as it looks like matrices, the table, and that's why we call it as a matrix. So nothing other than that, and since we see the error values, as a part of this matrix, and that's why we call it, otherwise called, we also call it as an error matrix. Okay, so don't get confused with the metrics and matrix. So one of the classification more, the task matrix is nothing but the confusion matrix or error matrix. That's all. So we go on to talk about what is TP and FP and all that. I was talking about true positive and false positive, false negative, and see, I'll take this example. See, there is no fire, but what happened? The alarm actually alerted the people, and what happened then? We call it a false positive, because there was no fire, but what happened? Alarm actually alerted the people. That is false positive. And for example, we give another one. Let's say there is a fire and still there is no alarm, and in such case what we do is we call it as a false negative. And this stuff, I was talking about the healthcare use case. This is what I was talking about in healthcare use case. What happens? The person is affected by COVID-19. Again, what happens? The system get to classify he is not affected by COVID-19. That's such dangerous stuff. So we should we work on it in such a way we never end up with such kind of results. So that is why false negatives are such important to healthcare machine learning use cases. So these are some of the values that has been taken as a part of it. And again, true positive, we get to see both of the places. There is a fire, so we get an alarm. Again, that is a true positive. So of course, what we do, such kind of outcomes we either get through the test validation, the test data set, or through the validation data set. And through, when we get to have the validation data set, we use the cross validation technique, that actually where we have I haven't talked about the k-fold cross validation. What happens there? We have different iterations, that again depends upon the folds of validation data set. So what we do, we get to choose a set of data set, and then we iterate in the sense the next fold, k times we iterate it, and that is where we incrementally choose the the foldings of the data set, and where we take that values for evaluating the module instead of taking it from the training data set. And when we do take it from the training data set, we end up getting the underfit model. So again, test data set is again a different one. We after validating the model and after evaluating the model, we once again go on to train model. Usually hyperparameter tuning that I talked about it, right? So usually fall in these two places, especially in the validation data set, such hyperparameter tuning happens. So hyperparameter tuning, in the sense the fine tuning the models and all that stuff, happens usually in the validation data set, not in the training data set. So test data set is often used for testing the model if it is yielding the right data set, even with the new data set. For example, we train a model with what we with the data what we have already have, and for example another new customer comes in and he ingested his own data, that is a new data, and with that data we call it as a test data. And what happens, that test data again tested the model, and if it yielded the right results, it is a we have trained it correctly, which means, so that talks about that is a good sign, we would say. Make a prediction for each row in a test data set, and it's again when we talk about the tabular data sets and structured data. When we talk about structured data, the tabular data set, and we go on talk about this, the number of correction prediction for each classes again fall in the the labels wise. So multi-class label classification we have, single class label, multi-label classification we have. Again, there are this kind of different stuff we get to meet, but at this point this is out of scope for us. So the number of incorrect predictions for each classification organized by classes, the class that was predicted. The class is nothing but, I would say, whether it is a dog or, for example, if I have three different categories here, say dog, cat, and another animal, say tiger. So here we have three classes. This is this is what we call it as class, and the label is nothing but for which one we need to figure out. I mean, if we wanted to only figure out with, identify or detect with only the dog and cat, we only to choose only those two classes, and we call it as a labels, and we leave other class as a, we don't call it as a label because we don't want it to predict the tiger here. That's why it is an irrelevant stuff for us. So here, moving ahead, how we go about calculating it is again mathematical stuff. We use that true positive and the false positive and true negative and false negative stuff, and this is how we get to have the errors here. And conclusion, what happens here, see, as per this example we see here, so whenever men classified as a man as 3, that is actually value that we are giving it just for the sake, just for the example, for instance. So what happens, as per this given values, for example, we see it here, the conclusion, more errors while predicting men as women than predicting women as men. So it's just an example, let's not much consider about it now, but all you need to know is, if you get to know the confusion matrix, what it is and how it is, and this is how we interpret the confusion matrix. I mean, we understand it, we get to comprehend it like this. So for example, true positive, I was talking about it, alarm goes on in case of fire. False positive, this is again type 1 error we call, and what happens, alarm goes on but there is no fire. But again, false negative, this is again very critical, type 2 error, no alarm in case of even if there is a in spite of having place what is that, the fire in place, we what is happening, there is no fire. It's again such a dangerous stuff. But we do not get to consider such false negative. Again, let's take this use case. We type the email, right? So what happens when we type the email, what is the next predicted words? When we type the email in as a sentence, we get the other the upcoming words, right? So at that point we don't need to consider false negatives, because where we won't be having such impact in healthcare use cases, but of course we have that kind of impact. And again, true negative, no alarm, no fire, that again no problem. So true positive and true negative, of course. So this is how we get to make it in a confusion matrix. So n is nothing but a number of samples here. So how many number of data samples we have here? For example, how many data images we have, how many cat images we have. Those images are otherwise called as samples. I mean to say those images as a part of unstructured data. Okay, and again the structured data, the tabular data is quite again a different one. So the next one would be, and the examples, when we substitute the values in it, we get to calculate like this, and we will talk about how we go about calculating it and in the further slides. And next one, issues with this. What is the limitations of the confusion matrix? Why there are again different evaluation metrics when we have such confusion matrix in place? I already talked about it. We have only one, we are only having one fixed threshold value, because what happens in the real-time predictions or online learning predictions, more also in batch predictions we call, what happens in such places, we get to have continuous threshold. We get to change the continuously the threshold values because we need to have the high performing model, because we see that this threshold value is no longer it is useful for us. We get to change that, increase the threshold value. I told you already, the threshold value falls between 0 and 1, and typically in industry they get to choose 0.5, 0.5 as a typical default threshold values. And here coming to confusion matrix, and the continuous changes threshold value will create new metrics each time. This is again quite challenging stuff, so that is why we the confusion matrix actually failed, I would say. So, and when we do not have such scenario in place, we do not worry about it. So we go on to use the confusion matrix. So n number of confusion metrics will make confusion. What happens as we go on to change new metrics upon the changed threshold, continuously changing threshold values, we get again different confusion matrix that will of course confuse everyone, including the one who is the programming, and the one who is. So these are all the stuff we get to see happening all over the places. And again, practically high threshold voltage, high threshold value, we choose it for training the model, and also that is also often used and for evaluating the better model. So that is why ROC, the another metric, comes into picture. We are going to see just what is that ROC. Now, as we get to see that summarizes the information of confusion metrics with changing threshold values. And what happens, ROC, we have a curve, and as we change the threshold value, and we also change the learning, what is that, the rates, and as we see move upon the loss and iterations, and we see or such ROC. Let me tell you what is that ROC too. So again, ROC is nothing but we call it a receiver operating characteristic curve. So which means that a curve of true positive rate, we would say the TP rate in short, versus false positive rate, FP rate. So this is a ratio, the ratio of this true positive rate to false positive rate at a different classification threshold. This is important. I mean to say threshold value is nothing but, so basically we call a threshold, a value, a threshold value. What happens, that is where we get to choose the right parameters. So upon choosing the right metrics at that point, the threshold value in the curve, that gets to form a curve actually, as I'm talking about, it is a kind of true positive rate, TPR, versus false positive rate, FPR. So as we have such, it's just a value on the curve, that's all. Threshold value means it's a minimum value, okay? Minimum value, that is where we get the parameters in place. And as we go on to project, as we go on to market on the the latent space of the data set, I mean to say the space, and we get to create the graph there. And such graph we call, such curve we call it as receiver operating characteristic curve, or OC curve. Okay, and in our OC curve, y is equal to true positive rate. I talked about it already, and x is equal to false positive rate. So we summarize this version of confusion matrices. Okay, so matrices, confusion matrices, we get to have different versions of confusion matrices with continuous changing threshold value. I think with this we are stopping the session. Thanks a lot. Stay safe. Bye bye.